1. The concrete strength of the inspected pile shall not be lower than 70% of the design strength, and shall not be lower than 15 megapascals, and the age shall meet the requirements of the specification. 2. The pile head needs to be handled in strict accordance with the specifications. It is recommended to prepare a variety of vibration excitation equipment and hammer pads to identify the reflected signal of defects in different parts. 3. The transducers, sensors, and other equipment used in the test should be handled with care during installation and transportation. When using equipment, should operate accordance with the requirements of the instructions.
That's all for the third part. Now we will have 10 minutes rest. After 10 minutes, we will come to the final part of this course, low strain curve analysis. We will further learn about low strain testing through some engineering cases. Now in the rest time, I will make a brief introduction of RSM Pi Integrity Tester. All the friends now in the live room will enjoy the biggest discount within 1 month. RSM has two types of PIT testing equipment. One is the RSM PRTP. It has two channels which can connect two sensors to get two signals at one time, and it has more uses. The other is RSM PRTR, which is more cost-effective. RSM PRT equipment is applicable to ASTM standard. In China, our company is the chief editor of technical code for detection of building foundation Pi, Pi dynamic tester, and Pi low strain instrument. RSM PRTP low strain Pi integrity tester is a brand new dual channel PIT testing equipment, and it is independently developed and designed by Cineroc. It is exquisitely designed, user-friendly, and very simple to operate. Dual acceleration sensors to connect the signal at the same time. It is suitable for a variety of low strain method testing specification, including dual speed method and transient response method. When a single top mounted acceleration sensor is connected, the conventional single-speed testing can be completed. When two side-mounted acceleration sensors are connected, the dual-speed testing can be realized. When the top-mounted acceleration sensor is connected and the hammer acceleration force measurement is carried out, the transient frequency response testing can be achieved. RSM PRT series uses the instantaneous floating point amplification technology, can take into account the distortionless acquisition of strong and weak signals. The 3D correction function, by which we can get a more accurate signal and the defect can be located accurately. And the test result can be analyzed, and the defect location can be calculated on-site. And the software is very simple to use. And our equipment is newly upgraded in 2022. The appearance of the host is more fashion, and it uses ABS plus PC engineered plastical material with high temperature resistant design and IP65 dust-proof and waterproof design. And the battery is super thin and is removable, ensuring long-time work. RSM PRT series adopts industrial-grade competitive touch screen instead of old resistant screen, which is much more smooth and soft and more precise to operate. On-site, it can adapt to strong light environment. And the RSM Pi integrity tester are widely used in China. Many important projects are choosing RSM brand for its reliable performance and professional and considerable service. Here, show you a real project in China. It is an express bridge project. The pi length is 50 meters, pi diameter is 1,300 millimeter, concrete design strength is C30. Low strain detection of foundation pi should be carried out according to technical specification through the integrity detection of low strain reflected wave method. According to above images, you can see the report, and the reflection at the pi end is obvious. There is no defect reflected wave, and the concrete wave velocity is within the normal range. According to the specification, the integrity of the pi body can be determined as class 1. And that's all for the instrument instruction. For more detail, we will send you document by email. If you have any question for our equipment, you are welcome to contact us at any time. For our company was established in August 2008. This year is our 14th anniversary, so we bring the biggest discount for PIT testing equipment, and is sold only $3,999, and the valid date is until September 28, 2022. And we can promise you it is the lowest price that it will never available again after this time. And $3,999, and see what you can get. RSM PRTR Pi Integrity Tester 1 set, and you can get 2 sensors. We will send you 1 more for backup. And the warranty extension, you can get 2-year warranty, and the free training, 1-to-1 online technical support, and lifetime upgrade for software. And please remember, the special offer is valid just for 1 month. After this period, the price will be back to $6,200. And we can promise it is the lowest price you can get. If you can buy a more lower price through any channel, we can make up the difference. If you are interested, you can connect the Cinerock or our authorized dealer in India. We have sent the connect number and email in the chatting box for your conference. Now our class will continue, and we will show you some typical cases of PIT testing. And after that, we are going to give you a demo indoor. We prepared a model pi with a defect, and we will detect the pi to see whether we can locate the defect accurately. Again, if you have any question during the class, you are welcome to send them in the chatting box. If we cannot answer it all day, we will continue answer them by email. We are very pleasant to have more communication with all the friends. Now the class begin.
This lesson will consist entirely of low-strain curve analysis. For a better understanding, we will gradually analyze from the theoretical curve, model rod curve, and model pile curve to verify the accuracy of low-strain PIT testing. The model of theoretical pile is based on a hypothetical condition. That is, the material of pile body is uniform, and there is no medium interference around the pile. The curves we will talk about later are based on friction piles. The left side is the model pile, and the upper right side is the velocity time history response curve. Generally, it is less seen below, which is a stress wave propagation roadmap. Because this pile is a friction pile, it will get a reflection in the same direction at the pile bottom, which is the same as the phase of the pile head, from the path curve of stress wave propagation. The stress wave will reflect on the pile bottom. According to the specification, it can be concluded that the stress wave propagated twice the pile length in this time period. The average wave velocity of the pile body can be obtained by dividing the time by twice the pile length. This is a bulging pile, which means that the wave impedance, or cross-sectional area at the bottom of the pile, is greater than the pile body. When the wave impedance increases, an anti-phase reflection will occur at the corresponding interface. So there is a reverse reflection here. Because the pile is a friction pile, there is a reflection in phase at the bottom of the pile, which is the curve of an bulging pile. In the actual testing site, we may collect another kind of curve, which is opposite to the direction here. That kind of situation is the rock socket pile containing sediment. This is an end-bearing pile. The strength or wave impedance of the bearing layer at the bottom of the pile is larger than that of the pile body, and its bottom reflection is opposite to the incident wave. This is a necking pile. What we see is that the pile reflects the reduced diameter in the form of cross-sectional area. This necking is a whole necking to the end, and there is no restore process in the middle. So it will produce a reflected wave at the corresponding necking position, and the reflection is in the same direction as it. Since it is close to the pile top, multiple reflected signals will be generated. Here we can see the primary, secondary, and tertiary reflections of this defect. And even after the pile bottom, we can see 4 reflections. So how do we generally look at multiple reflections? The time difference between the first reflected peak and the incident wave is almost the same as that between the second peak and the first peak. And the time difference between the third peak and the second peak is almost the same. This is a bulging pile. We can see that it is expanded to the bottom. The expanded pile will also produce reflection on the interface. Its reflection is because the wave impedance increases, and an anti-phase reflection wave will be obtained. The odd number of reflections are anti-phased, and the even number of reflections are in the same direction. The latter is always the reflection of the previous anti-phase. So it is its reverse. It is its reverse. And the third is the second reverse. So odd times are antiphase and even times are in phase. These phase directions are for incident waves. This is the case of the restoring after the necking of the shallow part. The position of the necking will produce a reflection, and the process of restore will also produce a reflection. So the reflection of the same direction represents the necking, and the reflection of the reverse position represents the restore. When we collect such a curve on site, we often feel it difficult to judge. In this case, it is suggested to increase the excitation frequency and try to separate the reflection of this defect from the front wave. The necking in the middle is easy to judge, because it is completely stripped from the inside of the front wave. Through this path map, we can see that this is the secondary reflection, which is the reflection of the pile bottom. This is a deep shrinking pile. This situation only moves the reflection phenomenon we just mentioned to the pile bottom. Its secondary reflection will only appear behind the pile bottom. probably at this position. So it is difficult to judge its secondary reflection. Of course, if the acquisition time is long enough, you can also see its secondary reflection. This is the pile with bulging in the middle. Through the propagation path of the stress wave, we can see that the antiphase reflection occurs at the enlarged position, and there is the same direction reflection at the restore position. Its secondary reflection is here. This is the primary reflection of its enlarged diameter, and the reflection at the bottom of the pile is here. This curve can only be studied in theory. No one can judge this curve clearly in the actual construction site, because it is based on the absence of external interference. This gradually expanding part deviates from the baseline, which is the process of restoration, affected by the soil around the pile and other aspects on the site. This curve itself deviates from the baseline, which is difficult to judge clearly. Therefore, this curve can only be studied in theory, which is difficult to judge. This is a shallow enlarged pile. Since there is no external influence, a reverse primary reflection, secondary reflection, tertiary reflection, 4 times and 5 times, are superimposed immediately after the incident wave. Pay attention to this curve, which is often measured in field tests. We should distinguish whether it is an oscillating curve or a defective front. This is a typical 4-type pile in the standard low-frequency large vibration curve. It is the in-phase reflection caused by the defect in the very shallow part, which is superimposed on the signal of the first wave, making the first wave into a low-frequency signal, which we will see later. In the actual project, some of our customers will separate the reflected signal of the curve defect similar to low-frequency large vibration from the pile head signal by increasing the excitation frequency. This is a situation in which the pile body has 2 defects: diameter necking on the top and diameter bulging on the bottom. On the measured curve, it will be found that there are primary reflection, secondary reflection, and tertiary reflection of reduced diameter restoration in front. At the position of bulging, there is reflection of reverse position. It should be noted that multiple reflections of necking may be superimposed with bulging, resulting in signal confusion and difficult to judge. This is a pile with shallow bulging deep necking. We can see that there is a first reflection and a second reflection in the shallow bulging. And when the second reflection is not over, the reflection in the same direction of the necking is superimposed. This is the case that there are 2 necking positions on a pile. In the first necking, we can see the first reflection and the second reflection. At the third reflection, the first reflection of the second defect is also superimposed, causing its amplitude to be higher than that of the second reflection of the first reflection, and the frequency width has changed. After reading the theoretical curve, let's look at some model bar curves. I suggest, if possible, you can make some model bars, so you can practice. Let's first look at a PTFE model rod. The rod is 1.5 meters long, 0.05 meters in diameter. And the wave speed is about 700 meters per second. A necking is made in the middle of the bar, which is fixed at the same position. This is a style drawing. What kind of curve have we measured on this bar? This is the incident wave of the rod head, the rod bottom, and the defect. This is close to the theoretical curve we mentioned earlier. The analysis shows that there is a defect at 0.92 m. We notice that the amplitude of this is lower than that of the bottom of the rod, because there is no external influence. So the degree of this defect is not very serious, and most of the energy can be reflected back through the pile bottom. The basic parameters of the second model rod are similar to those of the first one, but the reflection amplitude of this curve defect is larger than that of the rod bottom. Assuming that we represent the change of wave impedance by area, the area change of defect itself is very large. So most of the energy is reflected to the rod head, and the energy transmitted to the rod bottom is weak. Therefore, compared with the defect just now, the degree of this defect is larger. The defect is located at 0.97 m. This is also the same rod, which is complete. It's easy for everyone to judge the rod head and the rod bottom. There is a bulging near the bottom of the rod, and a collar is added. During the actual testing, we can see the incident wave of the rod head, and then there is an anti-phase reflection in the middle, which is similar to the increased wave impedance of the bulging. After calculating the wave velocity, according to the reflection at the bottom of the rod, it is judged that there is a defect here. Let's take another look at the collected curve of the model pile. Model piles are models that each place makes for examination or self-study according to its own work needs. This is a prefabricated square pile with a length of 6 meters. Because everyone considers the cost of model piles, they are generally not very long, and the pile diameter is not very large. Next, let's look at the curve. The first curve should be easy to analyze. This is a complete curve. But why is this place higher than this place? Because this is a pile placed on the ground rather than buried in the soil. There is energy loss when the pile is buried in the soil, and the amplitude of the pile bottom is low. The analysis of the second pile is a little troublesome. There is no problem with the pile head and the first defect. There may be some problems here. You may judge this place as bulging. We should pay attention to this defect. Its reflection amplitude is so high that some energy may produce secondary reflection. We can see its secondary reflection phenomenon in this place. But the latter part is another curve superimposed on it. So there is still a defect here. This is a pile with two defects. If the first defect has secondary reflection, it must be a serious defect. And the secondary reflection of the second defect is difficult to see. So it is a relatively minor defect. In the third curve, we can see that because they are prefabricated piles at the same construction site, we can see that there is a reflection in the same direction, and a reflection in the opposite direction in this place. According to the above curve, there is also a relatively large amplitude of the same direction reflection. So here are mainly these three defects. The first one is relatively small, so it is difficult to see the secondary reflection. And the secondary reflection of this one is close to here. So please be careful not to judge this as another defect. Let's look at another construction site. The cast-in-place pile is 10 to 13 meters long, and the pile diameter is relatively large, 1.2 meters. Let's look at its curve. The incident wave at the pile head is easy to understand, and the reflection in the same direction at this place is also easy to judge. The reflection at the pile bottom is relatively clear. Similarly, you may notice the reverse bit in this place. In fact, there is a process of secondary reflection in the early stage. As for the mud inclusion mentioned here, low strain has no ability to judge this situation. Sometimes it is necessary to make auxiliary judgments. According to the actual construction process, the second pile is relatively easy to judge, because there is a strong reflection here. According to our preset pile bottom signal, there is basically no signal, and the reflection of this is precisely his secondary reflection. So in fact, we didn't find the bottom of the pile. This is only the secondary reflection of the defect, which is a broken pile. The defect judgment of the third pile requires a little experience. We can see the second, third, or even fourth reflection. For low strain, we only need to judge the main defect and judge it. The previous minor defect can be abandoned. The whole pile is on the baseline, and there is almost no vibration. But we can find that there is a slight bugling in this place, and there is a slightly serious necking in this place, and the pile bottom is very clear. For the second pile, the incident wave at the pile head is very clear, and the reflection at the pile bottom is also relatively clear. The trend of the whole curve is superimposed here, with a slight co-directional reflection. So there is slight defect. For the third pile, we can also see the incident wave, which is reflected from the pile bottom. This is a reflection wave in the same direction. Let's look at another model pile experiment, which is a cast-in-place pile with a pile length of 12 meters and a pile diameter of 1.5 meters. This is due to the influence of the soil around the cast-in-place pile and the bearing layer at the bottom of the pile. So we can see that the reflection at the bottom of the pile is much weaker than that at the head of the pile. Unlike the previous model rod, the reflection at the bottom of the pile is stronger. Let's take a look at the second one. Because it is a construction site, the reflected pulse width has changed, and the pulse width and amplitude holding force here have changed. This is the position of the pile bottom. So this pile has two defects. The third curve is difficult to judge, because when we see such a curve, we will feel how there are so many reflections. Which ones are problematic and which ones are not? Please analyze it in turn according to our conclusions. First of all, we can see that there is an obvious decline process after this curve comes here, because its overall baseline is a development process. So this place is superimposed with an expanded signal, with the development of the curve. There is a homonym here, followed by another homonym. The amplitude of the latter one is higher than that of the previous one. The energy is attenuated, and the amplitude of its reflection is larger than that of the previous one. So its defect is larger than that of the previous one.
Now we will have a demo for PIT testing. These are our engineers, and this is Tom Zhou, and this is Patrick.
Hello.
We prepared a model Pi, and our engineers will show you how to connect, install the sensor, how to do equipment setting and the data connection. And this model is about 1.5 meters long. As you see, we made a defect necking down at about 0.50 meters from the top and 0.98 meter from the bottom. The wave velocity of this material is about 735 meters per second. Now we will make a demo to test the model Pi and to see whether we can locate the defect accurately. And first we need to connect the sensor with the equipment. And then we need to install the sensor to the Pi top. Now we need to switch on the equipment to set the parameter. We click RSM sampling and setting. There are a lot of parameters and you need to set it before your sampling. Okay, and the setting is okay, and then we click sampling and to excite the signal by hammer on the Pi top. Okay, now we get the signal and we can do a basic analysis on the host. And we can open the result we just tested, and we can clearly see the Pi top. The Pi top. And the Pi bottom. And the defect, and we can see the position of the defect is 0.48 meter. And now let's measure the position of the defect with a ruler. And we can see
Yes, yes,
0.49. Yeah. And we can see the test result and the measurement are almost the same. Now we turn the model rolled over and perform a test from the other end. And we repeat the test and to see the result. We turn it over. Let's measure it again. We install the sensor. And to do sampling again. Okay, we can see the test result. And we can do an on-site analysis and locate the pi button and the defect. And we can see the defect location is 0.97 meter. And now we measure the model pi and to see whether it's accurate or not. We can see the location is 0.90 almost 98 meter. Yes, we can see it's also very accurate. The test results of Synolog equipment are very accurate and reliable. And after the sampling, you can export the data and further analysis the data by the analysis software on computer. For time limits and our question we didn't answer will be sorted out after the training course and shared with you in the form of documents by email. And I'm very glad to spend a very meaningful 2 hours with our engineers today. And I believe that you can get something from today's course. And the training certificate will be issued to you by email within 2 weeks after the training course, and only for our signed engineers. And finally, I would like to thank all the participants today. If you have any advice for our training course, you're welcome to contact with us. We will be appreciated. And that's all for today. I hope we can meet next time. And thank you again. Bye-bye.
Bye.